What if I told you that one of the biggest, most powerful ideas in all of math, I'm talking about differential calculus, was basically invented to solve two really old problems? One was a philosophical brain teaser about whether we can even move, and the other was a geometry puzzle about curves. So let's start with the philosopher. We have to go way, way back, about 2,500 years, to a Greek philosopher named Zeno of Elea. He came up with this famous paradox. To get anywhere, say from point A to point B, you first have to go half the distance. Okay, makes sense. But then you have to go half of the remaining distance, and then half of that new remaining distance, and on and on and on forever. So Zeno's conclusion from this was, well, it was pretty wild. He basically argued that to get anywhere, you'd have to complete an infinite number of tiny little journeys. And since finishing an infinite number of tasks in a finite amount of time, well, that should be impossible, right? So he just concluded that all motion must be an illusion. It's a great question, isn't it? I mean, if Zeno's logic holds up, how is anything moving at all? This wasn't just some clever riddle. It was a seriously deep problem that had thinkers totally stumped for 2,000 years. And the reason why is because they were missing the right kind of math to explain it. Okay, so while the philosophers were stuck on that whole motion paradox, mathematicians were wrestling with a totally different, but as we're about to see, a deeply connected problem, the tangent line. How in the world do you find the exact slope of a curve at one single solitary point? The old school definition, going all the way back to Euclid, is probably what you remember from high school geometry class. A tangent line just kisses a circle at exactly one point. Easy enough? The trouble is that definition just completely falls apart when you start dealing with more complicated curves. Ones with a wiggle or an inflection point where a line can touch at one spot but still cross right through the curve. The solution didn't just appear overnight. It came in pieces. Back in the 1630s, this brilliant guy, Pierre de Fermat, came up with a method he called inadequacy. Instead of trying to find the slope at just one point, he'd compare the point x to another point that was just a tiny, 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 tiny distance away, which he called x plus e. And by making e practically zero, he got an incredibly close approximation of the tangent. This really set the stage for Newton and Leibniz to build the whole system we now call calculus. And this really gets us to the heart of the problem. Think about it. The slope formula you've known forever, rise over run, it's built on having two separate points. So how on earth are you supposed to calculate the slope at just one single instant? You can't just put the same point into the formula twice. You'd get 0 divided by 0, and the universe would break. Well, not really, but in math it's meaningless. The answer, the absolute game-changing concept that finally gave us the language to solve both of these ancient problems, is the idea of a limit. A limit isn't about where you are, it's all about where you're headed. It's the value a function gets closer and closer and closer to as your input gets closer and closer to some number. And this is the key to Zeno's paradox, too. The limit lets us show that an infinite number of ever-shrinking distances can actually add up to one single finite number. Those infinite steps don't take infinite time after all. All right, so that's the theory. Enough talk. Let's actually see how this brilliant idea of the limit works in practice and finally solves our tangent problem. So we're going to roll up our sleeves and work through a real example here. Our mission, should we choose to accept it, is to find the exact instantaneous slope of this parabola, f of x equals 15 minus 2x squared, right at that single point where x equals 1. So how do we do it? We're going to do something that feels a bit like cheating. Since we can't use just one point, let's use 2 points that are ridiculously close to each other. Check out this table. It shows what happens to the slope as we pick a second point that just inches closer and closer to 1. Look at the numbers coming from the right. We go from -6 to -5 to -4.2. And look at the values from the left. -2, -3, -3.8. Do you see what's happening? They're both squeezing in on one specific value. And there it is. The number that our slopes are homing in on from both sides is -4. That is the limit. And that, by definition, is the precise, instantaneous slope of our curve right at x equals 1. It's such a beautiful illustration of how powerful the limit is. But, looking at a table is one thing. In math, we like to prove it. And we can, with some good old-fashioned algebra. We just set up our slope formula. Then we simplify and factor it out. And then we get to the absolute best part, step 4. That pesky x minus 1 term in the denominator, the one that was causing all our problems by giving us a 0, it just cancels out.
we're left with a much friendlier expression, -2 times 1 plus x. Now we can just plug in 1, and what do we get? -4. Perfect.
Okay, so this isn't just some neat trick to solve a geometry problem. The real magic, the big leap, happens when we realize that finding the slope of a tangent line is the exact same thing as finding an instantaneous rate of change. Think about it like this. The slope of a secant line, the one that connects two different points, that's like your average speed over a whole road trip. But the slope of the tangent line at one single point in time, that's the number on your speedometer at that very instant. One is the average over an hour, the other is what's happening right now. And why does that matter so much? Because that idea of right now, that instantaneous rate of change, well, it describes pretty much everything important happening in the world around us. I mean, in physics, it's literally the definition of velocity and acceleration, but it goes way beyond that. In economics, it's used to find what's called marginal cost, the exact cost of producing just one more item, which is crucial for businesses. In biology, it's used to model how fast a population is growing, or a virus is spreading at any given moment. It's everywhere. Now, for anyone out there actually studying this stuff, here are a couple of classic traps to avoid. First, if you ever set up the formula and get 0 over 0, don't panic. That's your cue to do more algebra, just like we did to cancel out those terms. And second, always remember, the limit is about the journey, not the destination. It's what the function approaches, which isn't always the same as the function's actual value at that point. So if you only remember one thing from all of this, let it be this. The geometry puzzle of the tangent line and the real-world physics problem of instantaneous velocity are, deep down, the exact same mathematical problem. They are two sides of the same coin, and they're both solved by this beautiful, powerful idea of the limit. So this one single idea, the limit, gave us the tools to finally put Zeno's 2,500-year-old paradox to rest. It showed us that an infinite series of smaller and smaller steps can add up to a single finite path. This idea turned philosophy into a solvable equation and paved the way for understanding everything from planetary motion to modern economics. And it just makes you wonder, right? What seemingly impossible problems are we facing today that are just waiting for the next great mathematical idea to come along and unlock them?